Since you know mu and sigma square, using the theorem 1, you can find out the moments of Zn, first and second order moment, expectation of Zn and variance of Zn. Since mu is equal to 1, the expectation of Zn will be 1, variance of Zn will be n times sigma square. In this problem, the sigma square is 2 by 5. Therefore, mean of Zn is 1, variance of Zn is 2n by 5. Now, we are going to discuss the very important concept called probability of extinction. If Zn is equal to 0 for some value for n is greater than or equal to 1, then Zm will be 0 for all m greater than or equal to n. And also, the conditional probability of Zm is equal to 0 given Zn is equal to 0, that will be 1 for all m greater than or equal to 1. We say that the branching process is extinguished when probability of Zn is equal to 0 will be 1 for some value of n. Now, we discuss the probability of extinction in theorem 3. If mu is less than or equal to 1, then the probability of extinction is 1. If mu is greater than 1, then the probability of extinction is the positive root less than unity of the equation h of s equal to s, where h of s is the probability generating function of Z1. Here we consider a Galton-Watson branching process Zn with offspring distribution Pk, and the Pk forms a probability mass function for the random variable Z1. If mu is less than or equal to 1, then the probability of extinction is 1. If mu is greater than 1, then the probability of extinction is the positive root less than unity of the equation h of s equal to s. That means you have to solve the equation h of s equal to s. From that you can get the probability of extinction. Here mu is a mean of the random variable Z1. Let us see the proof. Let dn be the probability that extinction occurs at or before the nth generation. Hence, dn is nothing but the probability of Zn is equal to 0. We know that d naught will be 0 because we made the assumption Z naught is equal to 1. Now, we will find out dn plus 1. dn plus 1 is nothing but, by the definition, it is dn plus 1 is nothing but probability of Zn plus 1 equal to 0. We can write a probability of Zn plus 1 equal to 0 using conditional probabilities. That is same as probability of Zn plus 1 is equal to 0 given Zn was 0 multiplied by probability of Zn is equal to 0 plus probability of Zn plus 1 is equal to 0 given Zn is not equal to 0 multiplied by probability of Zn is not equal to 0. We know that probability of Zn plus 1 is equal to 0 given Zn is equal to 0, that is equal to 1. Therefore, this will be 1 times the probability of Zn is equal to 0 plus probability of Zn plus 1 is equal to 0 given Zn is not equal to 0 multiplied by probability of Zn not equal to 0. Obviously, this will be greater than or equal to probability of Zn is not equal to 0 because you are adding some probability plus probability multiplied by probability of Zn is not equal to 0. Therefore, this quantity will be greater than or equal to probability of Zn not equal to 0. This quantity will be, this is same as 1 times probability of Zn is equal to 0 plus probability of Zn plus 1 equal to 0. Given probability of Zn is not equal to 0 multiplied by probability of Zn is not equal to 0. Obviously, this quantity will be greater than or equal to 0, the second term. Therefore, the whole result will be greater than or equal to probability of Zn equal to 0. You know that probability of Zn is equal to 0 is nothing but dn. Therefore, dn plus 1 will be greater than or equal to dn. This is true for n is equal to 1, 2 and so on. Hence, the d0 will be 0, d0 is less than or equal to d1, d1 will be less than or equal to d2 and so on. And since the dAs are the probability of extinction, therefore, that will be less than or equal to 1. Hence, dn is a sequence and upper bound sequence. Dn is a increasing and upper bound sequence. There exists d, that is nothing but the limit n tends to infinity of dn, and the d is belonging to the closed interval 0 to 1, and d is the probability of extinction of the process. Now, we will find out what is the d. You know that dm is nothing but probability of Zm equal to 0, that is nothing but summation over j, probability of Zm is equal to 0 given Z1 is equal to j multiplied by probability of Z1 is equal to j. You know that probability of Z1 is equal to j is nothing but Pj. Therefore, the dm is nothing but summation over j, probability of Zm is equal to 0 given Z1 is equal to j multiplied by Pj. We know that probability of Zm is equal to 0 given Z1 is equal to j is nothing but probability of y1 plus y2 and so on, yj is equal to 0. Since y's are IID random variables, that is nothing but probability of y1 is equal to 0, y2 is equal to 0 and so on, probability of yj is equal to 0. That is same as the probability of Zm minus 1 equal to 0 whole power j. That is nothing but d suffix m minus 1 power j. Hence, you can substitute this result in this equation. This conditional probability is nothing but d suffix m minus 1 power j. Therefore, dm will be summation over j d of m minus 1 power j Pj, and that is nothing but the probability generating function of dm minus 1. So, hence we get dm is equal to h of dm minus 1. Since dm tends to d as m tends to infinity, the value d satisfies the equation s is equal to h of s, because dm is equal to h of dm minus 1. Therefore, the value d satisfies the equation s is equal to h of s. Note that the solutions to the equation s is equal to h of s represents intersections of the graphs of y is equal to s and y is equal to h of s. So, the d will be probability of extinction, and we are not going to discuss further more about how to solve s is equal to h of s and finding the probability of extinction. We will consider the third example. Zn be the sequence of random variable which is a Galton-Watson process with the offspring distribution Pk. Similar to the example 1 and 2, P0 is equal to 1 by 5, P1 is equal to 3 by 5, P2 is equal to 1 by 5. Already we got the mean of Z1, that is equal to 1, therefore this is a critical Galton-Watson process. Now we can find out the probability generating function of Z1. Using this, one can find the probability of Z is equal to, or we can find the distribution of Zn also. For instance, we find a probability of Z is equal to 2. For that you need the probability generating function of Z2. That means you should know what is the probability generating function of H2 of S. With the help of H1 of S and H of S, one can find the H2 of S. That is what we have proved it in the theorem 2. Hn of S will be Hn minus 1 of H of S. So here we put n is equal to 2, find the probability generating function of Z2. Using the probability generating function of Z2, we are finding the probability of Z2 is equal to 2. So probability of Z is equal to 2 will be H2 double dash of 0 divided by 2 factorial. So first you find out H2 of S, that is nothing but H1 of H of S, that is same as H of S. So replace S by H of S in the H of S expression, that is 1 by 5 plus 3 by 5 times S plus 1 by 5 S square. So replace S by H of S, so you will get H2 of S. Once you know the H2 of S, you differentiate twice, then substitute S is equal to 0, then divide by 2, you will get the probability of Z2 is equal to 2. Since mu is equal to 1, this is a critical Watson process. By using theorem 3, we conclude the probability of extinction is 1. Theorem 3 says if mu is less than or equal to 1, then the probability of extinction is 1. So since in this problem the mu is equal to 1, hence by theorem 3 the probability of extinction is 1. So in this lecture we have covered the definition and the examples of branching process. In particular, we have discussed the Galton-Watson discrete branching process. We have discussed the probability generating function of Zn. We have discussed the mean and variance of Zn. Also, we have seen 3 examples through that we found the conditional probability, probability generating function, mean and variance of Zn. Finally, we have discussed the probability of extinction for the Galton-Watson process. In the next lecture, we are going to cover the another important branching process, that is a Markov branching process, which is a continuous type branching process. In this lecture, we have discussed a discrete type branching process, that is a Galton-Watson process. In the next lecture, we are going to cover continuous type branching process, that is a Markov branching process, and some more important branching processes. Here is the references.